out to you on Moodle. So if you scroll down to, I think we are in week, what week are we in? 10, 11? Okay. Did you turn in your fiber? If you haven't done so and you have it, please turn it in. This is for +5, so it's a very valuable homework for an extra credit. As soon as I get everybody's yes, I have it. I have yours. So after I get everybody's, I will, this is hidden for now, but I will unhide it so that you can see the key for that question. And also, you have a practice problem set for pH and titratable acidity. So we'll start this today, and I will continue with this lecture on Friday. And this is going to be part of your exam on Monday. So this practice would be nice to try and solve. It will give you some practice as you study as well for the exam. And this is again for +5. See, the opportunities I'm giving you for extra credit is try to encourage you to actually practice. So make use of that. I will post the key once you turn it in. It's up to you. You can give it to me on Monday or Wednesday before Thanksgiving. So it's up to you. I'll leave it open. You have till next Wednesday to turn it in. Okay, I also want to remind you for your lab reports, I noticed some of you are not really looking at the examples I put online for abstracts and sample lab report. So use this resource. I need to sign in. Okay, sign me out.
While Pam's looking at that, I just want to remind everybody for their approximate analysis lab report, that I have finished up the water ones, make sure you don't flip the difference between your CV and percent error relative. Make sure you know which one's for accuracy and which one's for precision.
Yes.
A couple people are still flipping those terms around,
Yeah.
which is definitely going to hurt you in your discussions.
Yes, and I noticed that as well in the when I was grading your AA, that some of you are using CV for accuracy still, which is using standard deviation for precision. You should use a CV. Jeshu, you're going to come back and ask me, I know. So listen to what I'm saying. CV is for precision, percent relative errors for accuracy. That's a good point, Jessica. Okay, so these are the resources. Unfortunately, I did not find a good sample lab report in AA. I'm going to have to dig one from previous years to put up. But anyway, use the GC and HPLC to look at abstract and what the abstract should include. Some of you are still not doing the abstract correctly, which is you still have the lab report that is due this Friday and one other lab report that is full lab report on fat characterization. So use this resource so that you have something to go back to in order to have an idea what the abstract looks like. Okay, another resource that I want to make sure that you guys are aware of. I already tell you this every time I send reminders, but make note that I put the key for everything that you have been examined on so far, and not just that. I put the key up for sample quizzes and exams. So again, these are good resources for you. The exam is coming up on Monday. The quiz, the last quiz that you've done was not a really good. Some of you missed a lot of points. I had to go back and try to give half points here and there when you are actually close to what the key is, but still the average was low. But the good news in this class, you have 950 points plus extra credits. So if you didn't do well on this quiz, that's okay. You can still get a good grade. If you do well and you have one more exam, one more quiz, a final, and several lab reports. So you can still catch up on grade. but use the resources. And I also have the key for the questions of your lab report. And if you have not noticed already, a lot of questions in your quizzes and exams are based on lab reports and questions directly from the lab report. So, lab report question keys, I have everything up to date except for, of course, the ash, fat, and protein, because you still have to submit that this Friday. And when you submit that, I'll put the key up for you. So, and I want to remind you, if you have any questions over the weekend while you're studying for the exam, I'm here Saturday and Sunday this weekend, working long hours and a couple of deadlines, so you can come see me or email me or call me. I'll be happy to help you. Okay, I'll be camping here this weekend, so. Okay. So that's all. And we can start on the new topic. This is chapter 13 in your textbook. Oh, one last thing Amy just brought up is the participation points. Some of you are doing really well that if you raise your hand, I'm ignoring you. Andy is an example. And some of you really not doing that great. Again, remember, this is just to have an atmosphere of discussion. It's not to twist your arm. It's just to have you be involved in the lecture. So, like I said, the question is welcome. Any question is a good question. Don't think it's a dumb question. There's no dumb questions. And answer. Even if it's a wrong answer, I don't expect you to know the correct answers. That's why you're in class. So, just talk. Talk to me. All right. The following is true about food or organic acids. They are weak acids, have good buffering capacity, can buffer at multiple pHs. Nobody wants to volunteer. John.
I think all of the above.
What about you, Claire?
I was going to guess all of the above.
Well, that's a legitimate guess. So yes, it is all the above. They are weak acids. By weak acid, we mean they do not dissociate completely. That means organic acids are usually 3% dissociated. When we say dissociated, that means they lose their proton. So they are conjugate base and a proton in solution. Only 3% in a solution is dissociated of an organic acid. That's why they're weak acid. They are reluctantly giving you their proton. They do not want to give the proton. That makes them a weak acid. Have good buffering capacity because they exist as an associated and dissociated. They can, if you titrate with a base, they will reluctantly give you their proton. And if you titrate with the acid, they will capture that proton. So they buffer. Can buffer at multiple pH. That is true. Why do you think? Let's see if any of you remember a little bit the chemistry of organic acids from your organic chemistry. What would make them buffer at multiple pHs? Have you heard of the term pKa?
Yes.
We're going to talk about it a lot today. What's pKa? It's good that you all heard about it, but do you remember what it is? Well, that's the tricky part. Yes?
That's the pH at which the concentration of acid is made.
Yes. pKa is the concentration, or the pH when you have concentration of your conjugate base equal the concentration of your acid that is not dissociated. That is correct. But what is unique about organic acid, they have multiple carboxyl groups, some of them. Like citric acid, for example, has 3 carboxyl groups. That means each carboxyl group has a dissociation factor, so that each one of them has a specific pKa value. That means each carboxyl group will buffer at a different pH based on their dissociation factor. Acetic acid has 1, but citric acid has 3, malic acid has 2. So depending on the acid you have and the number of carboxyl groups, they might buffer at different pHs. So that's why all of the above is correct. Now this concept is confusing to many. Let's see if there's one of you in this room that knows this. Should we give +3, whoever answered this correctly and explaining it?
If they explain.
They will get +3, okay.
It doesn't have to be right though. Oh, does it? Yeah.
Correct and with explanation. Come on, Amy.
Okay, so for the +3, yes, correct.
Correct with explanation.
Yes.
Okay.
You lose nothing by guessing.
You lose nothing. You get +2, but if it's correct with explanation, you get +3. All right, Amanda.
True, because other things in your food complex like that can change the sourness and density of the drink.
We'll hold off on telling you if you get +2 or +3. Let's see if others. Jeshu.
I think it is it is true.
It's true or false? Make up your mind.
True. Yeah. Because the acidity is kind of the measure like how many group of DH3O plus and pH you just like see like from base to acid at all.
I'll hold off. Who else? Ben.
False.
Why, Ben?
pH is the proton and the OH groups associations. If they're if an acid is completely deprotonated or they still have H groups attached. But titratable acidity means the only available H's. H plus is that to the titratable.
You were so close at getting +3. Okay, so whoever answered gets +2. The answer is false because Ben started right. pH has to do with the proton and OH minus. So the hydronium ion, which is water plus proton, is a hydronium ion, and you have the hydroxide ion. Together they give you the concentration of each, they give you the pH. The titratable acidity is the concentration of all the acid in your sample, whether it's dissociated or non-dissociated. So it's not the same. So if two drinks have the same pH, it doesn't mean they have the same titratable acidity. Or if two acids have the same titratable acidity, it doesn't mean that they have the same pH because they might dissociate differently. But the acidity is what contributes the most, or the total acidity is what contributes the most to the flavor. So if we say instead of the same, we would cross this to have different titratable acidity and different sourness intensity, then it becomes true. So here it is, so titratable acidity, so measure total acid concentration, that's what I said. And so it is, in other words, it's total acidity, whether it's dissociated or non-dissociated. And it affects the flavor. And it's an indication of maturity because as the fruit ripens, the concentration of acid becomes lower and the concentration of sugar becomes higher. So pH also is a measure of the free hydrogen ion. So hydrogen or the proton combines with the water molecule and gives you a hydronium ion. So in the presence of water and the proton, a free proton, you get a hydronium ion. And then it's a measure of the active acidity. That means the dissociated protons. And what does, okay, so acidity is related to flavor and maturity, but what does pH affect? What kind of reactions in food? Or influence what in food?
Maybe enzymatic browning.
Enzymatic browning is one example of enzymatic reactions.
Oh, no, it's
You want to say the same thing? I saw
yeah, same thing.
protein precipitation and curd formation, like in cheese or yogurt. Another important, Bill,
What about color?
y-
Something.
yeah, so there is the enzymatic browning. If you have, let's say, polyphenol oxidase, if you reduce the pH, then you stop the reaction or reduce the reaction, yeah?
Stability?
Stability in what sense? Which type of stability? Yes, stability, but what type of stability?
Shelf life?
Right, but what about shelf life?
Microbial.
Microbial. There you go. So microbial activity. So for example, acidic foods that have lower than pH 4.6, the pasteurization temperature and time is less intense than neutral food where you need higher pasteurization temperature and longer time. Okay. So here's an example where you have the same concentration of an acid. So you have 0.1 normal HCl and you have 0.1 normal acetic acid. So same concentration, same amount of acid, but because they're different acid, HCl is a very strong acid. That means it's very willingly giving up its protons. So it's almost 100% dissociated, and it gives a pH of 1 at 25 degrees C or room temperature. Whereas the organic acid, which is acetic acid, it has higher pH at the same concentration. So it's weak acid, about 1 to 3% dissociation, about 1%, but up to 3% dissociation. So this is an illustration that at the same concentration of an acid, you have different pHs. And that's the difference between a weak acid and a strong acid. Oh, and then this is pointing out, you're going to hear this. This is conjugate base. The dissociated acid is referred to as conjugate base. You'll hear that more as we go along in the lecture.
You say it again, same concentration but different
pH, right? So because this one is readily dissociated, a strong acid by nature readily gives its proton, and when you have a lot of proton, you will have less pH. Because it's a measure of active acidity or the measure of free protons. Okay, so from now on, we're going to have a lot of calculation based, giving you back to your entry-level chemistry. We have to remember certain concepts in concentration. And that will help when we derive equations. So you want to remember basic things in chemistry calculations. So molarity, moles of solute per liter of solution. So I expect you to know these for the test and the final. This is review. You guys already know this. Just review, and we're going to use it quite a bit from now on in the semester. Normality is not very common as molarity for some of you. It's like, what is normality? Normality is the number of mole equivalent of a solute per liter of solution. Mole equivalent is really, in this example, acid base, it refers to the proton and hydroxyl group transfer. If you don't have proton or hydroxyl group, you look at electron transfer. How many electrons are transferred? Then that would be the number of mole equivalent. So for example, in H2SO4, you have 2 protons. So the number of mole equivalent of H2SO4 is 2. HCl is 1 because you have 1 proton. NaOH is 1 because you have 1 OH. Calcium hydroxide is 2 because you have 2 hydroxyls. So it has to be directly related to the number of the protons and hydroxyl groups. So relating molarity to normality, so 1 molar solution of H2SO4 is equal to 2 normal solution of H2SO4. Because here you're looking at the number of mole equivalent is 2 per liter. So that's why it's 2 and this is 1. The molarity is 1. So normality equals X, which is the number of mole equivalent of solute, times the molarity. So always the normality is either equal molarity or greater. Equivalent weight is another term that you will come across. And that would be, and this is especially important when we calculate titratable acidity, because different organic acids will have different number of carboxyl groups. And because of that, you'll have different number of mole equivalent. So equivalent weight is important. It's the molecular weight divided by number of mole equivalent. So citric acid has 3, so you divide the molecular weight by 3, you get the equivalent weight of citric acid. Acetic acid is 1, so equivalent weight of acetic acid equal the molecular weight of acetic acid. So if we're determining titratable acidity, it's very important to know the number of mole equivalent, otherwise our calculations will be wrong. Percent concentration, you already know that it's the ratio of weight or volume. Sometimes or oftentimes titratable acidity is per volume or it's per gram. But if you have juice, it will be per volume. So it would be like grams per volume or milliliter per milliliter, 100 milliliter. And concentration, sometimes if it's very less than 1%, instead of reporting it as a percentage, we report it as parts per million, which is equivalent to milligram per kilogram or milligram per liter, or microgram per milliliter is also ppm. Parts per billion or parts per trillion. So you can go down to parts per trillion as well in reporting concentration. So equation of neutralization is what we will base our derivation of titratable acidity, and which is oftentimes you're titrating your acid with a base, right? So at equilibrium, you have milliequivalent of one reactant equals milliequivalent of another reactant. So milliequivalent of base equals milliequivalent of acid, for example. So a milliequivalent is milliliter of one reactant times the normality equals milliliter of 1 times normality. So if we know how much we start off, let's say 20 milliliter of juice, and we want to find the normality of the acid, we know the normality of the base we're using to titrate, and we'll just record the titration volume. When we reach equilibrium, the color of the titration will change. Then we know this, we know that, we know this, then we can calculate the normality of the acid. Oftentimes, this is used for dilution. This equivalence is used for dilution, starting with a concentrated base solution or concentrated acid solution, and you want to dilute it 10 times, 100 times, or get to a particular concentration that is diluted. So here's an example. You want to prepare 1 liter of 0.1 normal HCl from 12 normal HCl stock solution. What would you do using this equation to get this? Pull out a piece of paper, write your name, time to calculate, not to chat. You see me, you had it down. You have an answer?
I have an answer, I don't know if it's right.
Okay, tell me what you did.
Well, I did milliliters of the working solution, which is gonna be 1,000 liters times n of that, which is 0.1, equals 12
Yeah.
times x.
Yeah.
And you find x.
And then what do you do with that x when you find it?
So you convert it back to
So you take, let's say you get that x, which what was the x?
8.3 milliliters.
So you take 8.3 milliliter of the concentrate, and what do you do with it? Yes, you dilute it to 1 liter. So basically, you take that 8, you have the 12 normal HCl stock solutions. You get a volumetric flask that is 1,000 milliliter volumetric flask. You put a little bit of water in it. You add always add acid to water, not water to acid. So you put water in it, you add your acid, and then you make up to 1 liter, and then you get your 0.1 normal HCl. So when you get a question in exam like this, I want to see calculations right, but I want you to show me what you do next. When you get the final volume, what do you do with it? You want to explain the procedure of the preparation. So this course prepares you to chemical reactions. Those of you that will be taking chemical reactions next spring, you will be expected to prepare reagents independently. So this is just an exercise for you to know how to prepare basic reagents, taking into account molarity, volume, normality, number of moles. We're going to talk about more examples later. Also, if you go to grad school, you are expected as a graduate student to know how to prepare reagents. So this is your chance to learn this here. Even if you go to industry, right, Sonia, you prepare reagents in industry too. So yeah, so. Huh?
So you said you take the 8 mils and dilute it up to 1,000?
Yes, so you just bring a volumetric flask, you add a little bit of water, you add your volume that you calculated, and you bring up to 1 liter mark. So this is the calculation exactly as Becky, Erica. Why did I call you Becky? I have no idea where I got that from.
The bird in Finding Dory.
Becky, I'm from Finding Dory, that's right. I was watching it recently. But you don't remind me of Becky in Dory. Have you watched the movie? Becky is a weird loon bird. No resemblance. Okay. So you have the final volume that you want to obtain, you multiply it by the normality you want to obtain, you divide it by the normality of the concentrated solution, and then you get the milliliter amount of milliliters you need to bring up to 1 liter. Okay, so here we're trying to relate pH to concentration of hydronium ion and hydroxyl groups. So basic chemistry, we already know that acid is a proton donor, base is a proton acceptor. This in water becomes hydronium ion, and this is a hydroxide ion. At neutralization, you have the hydronium ion and the OH will give you just water. So this means that the concentration of hydronium ion by the concentration of hydroxide ions or hydroxyl groups will give you an ion product constant for water. At 25 degrees C or room temperature, this is about 1 times 10 to the negative 4, hence the range of the pH from 1 to 14, because pH is a log value. Okay, and this changes based on the temperature. That's why oftentimes when you are measuring the pH of a heated solution, so you want to make sure, or when you're titrating and you want to get a certain pH, you want to make sure that you are either at the right temperature, room temperature, or you have a thermostat, or yeah, that we do have pH meter with a thermostat, right, in our lab, to measure temperature, and accordingly the pH is impacted by the temperature. Okay, so at pH 7, the concentration of hydronium ion equals the concentration of hydroxyl ions. So basically it's 1 times 10 to the minus 7, 1 times 10 to the minus 7, you get that range of you get the constant, ion product constant for water. And the pH is, because it is related to the activity of the H, it is related to the concentration of the hydronium ion. There is POH as well, but we don't use it as often, we use pH. So, and that is equal minus log concentration of the hydronium ion. So at pH 7, this is minus log 10 to the negative 7 is 7, basically. So if we want to predict a concentration of OH groups in a 7-up that has a concentration of hydronium ion, as such, how can we predict the concentration of OH minus and the pH? So we apply this equation. So you want your calculator and you want the anti-log and log functions, so you can do the calculations on your piece of paper. You have it? What do you have, Sven?
OH exit 2.82 times 10 power 32 negative 11.
What was the pH?
The pH is 3.45.
Yes. Good. So basically you apply math. You substitute here to calculate this OH minus concentration. So you have, you know, the product ion product of water, and you get the concentration of hydroxyl groups, and the pH is minus log this. So you get the log of 3.55 on your calculator. It depends what type of calculator. You can do this in 1 step or you can do it 2 steps, depending on what your preference is. You can get log of each one separately and then add them, or you can get the log combined, depending on if you have a whatever type of calculator you have. I think graph calculator allows you to do it in 1 step, right? I think? No? You don't know? Yeah, I don't know either. I use regular calculators and I do them 1 step at a time.
Oh, yeah,
Yeah. Yeah, you could with a graph calculator. Yeah, okay. So if now the other way around, if you have a pH of 4.3, what would be the concentration of hydronium ion? So in this case, you need the anti-log function to do that. You have something, Joe? Okay. Again, you can either do it as step or as one function. You got something, Amanda? No? Anybody got anything? Yes?
5.0 times 10 to the minus 5.
Let's see. Yes. Very good. So basically you can also do it stepwise. I like to do things stepwise. Some of you might just do it 1 step. So I changed this number in a way that I get a whole number. So it's minus 4.3 is minus 5 plus 0.07. So I get the anti-log of minus 5 is 10 to the negative minus 5, and then the anti-log of 0.7 is 5, so it will be 5 times 10 to the minus 5. So this is the old-fashioned way with old-fashioned scientific calculators, but with the graph calculator you are probably able to do it in one step. So this tells you I'm old-fashioned. Okay. Got it? All right. So just a brief introduction about the pH meter. I don't like to go too much into detail. There is a lot about it in the chapter, but the main thing is just to refresh your memory of how a pH meter works. So it really measures the activity of the ion. So the ion, which is in this case a proton. So it is a relationship between the concentration and the activity coefficient. So you have the activity equals the activity coefficient times the concentration of the acid. The activity coefficient is related to the fact whether or not the acid is dissociated. So that's the math behind it. You don't do it, the pH meter does it for you. What the pH meter is measuring is change in voltage or the electric potential at a very small infinitesimal current. A very small current, because if you apply high current, it's going to affect the ionic state or the dissociation state of your whatever is in there, of your acid or ions. So you apply a very small current and then you monitor a change in voltage. So there is already a voltage because you have a reference electrode. So the reference electrode and the measuring electrode, when they are in a solution, a buffer solution or water or whatever, they are, well actually in a buffered solution, they have a specific potential. When you immerse that electrode or a combination of the two electrodes, then there will be a change in that potential, and that change is related to the concentration of the ion or the concentration of the active ion. So there is an equation which I don't ask you to know, it's in your book. You can go in and have a look if you're curious, and there's much more talk about how the pH meter works. So nowadays, oftentimes you have your reference and your measuring electrode in one electrode. So rather than having an old pH meter that has two electrodes that you would immerse in your solution, you will have one that is a composite of both your reference, where you have your reference solution and your measuring electrode, and that's when you have a constant potential, but when you have ions in the sample, then you will have a change in that potential, and that's how you measure the pH. There are guidelines to use the pH meter. You have to always calibrate your pH meter using at least 2, preferably 3 different pH solutions. Usually there are 3, 7, and 10. Right, ladies? In the back there? What are the... What do we use to calibrate our pH? 3, 7, and 4, or 2?
4, 7, and 10.
4, 7, and 10. Well, I was close. I said 3, 7, and what? 10?
4, yes.
So it's 4, 7, and 10.
Did I get plus 3?
No. Because you were not paying attention, neither one of you. Okay. So, yeah, we have to properly calibrate our pH meter before use. And we want to make sure that the electrode is kept clean. So if you're measuring a solution that is high in protein, for example, the protein may stick to the electrodes and might influence the next measurement. So you need to clean it with a solution that has pepsin enzyme in it. So if you have high fat, you will clean your electrodes with a diluted organic solvent or alcohol, methyl alcohol. Or regular cleaning would be with a dilute acid. So you want to make sure that you keep your electrodes clean and you keep them in reference solution when they are not, you don't let them dry basically. You want to make sure that they are stored in the reference solution, which is potassium chloride solution. So moving on to titratable acidity. So we talked about pH, talked about titratable acidity, which is the measure of the intrinsic or the concentration of the intrinsic acid in your food. And in order to measure the concentration of acid, you titrate with a base. So your most common organic acids are citric, malic, lactic, and tartaric. So citric is obviously present in citrus fruits, malic in apple, lactic in dairy, tartaric in grapes, for example. So inorganic acids that are often added to beverages, phosphoric acid is one. Carbonic acids actually, when like 7-Up, for example, has low pH because you bubble carbon dioxide in there, and carbon dioxide in water gives you carbonic acid, and that lowers the pH. In order to determine the endpoint at neutralization, or to get the final titratable acidity, we either use a pH meter to monitor the pH at equilibrium when we reach equilibrium, or we use an indicator. And in the lab, you're going to use phenolphthalein as an indicator, which turns red under basic conditions. So it will be colorless in your solution of acid, and then when you titrate with base at equilibrium, the last drop will turn pink. Here's the favorite equation that you really like. I know you, I can see it in your eyes. The excitement grew the minute I put it. Okay, so the Henderson-Hasselbalch equation. You're going to deal with it here, you're going to deal with it again in chemical reactions, and you probably dealt with it or seen it in food chemistry or somewhere else in your chemistry career. So, buffering. Because we're dealing with organic acids, we are dealing with buffering of these acids. So we need to understand this concept. So, and this is when, buffering is when the solution resists change in pH. That means you titrate with acid, the carboxyl groups that are dissociated are going to absorb the acid and the pH. The proton and the pH will not change, again, because the pH is a measure of free protons. So, the buffering occurs when you have a weak acid and its salt. That means your conjugate base is the salt, and the weak acid is the non-dissociated form of the acid. So when they're both present, so if you titrate with a base, you're going to get some proton release. If you titrate with an acid, some of the protons will be absorbed. So that's why the pH will be maintained. We already said that food acids are weak acids. You have up to maximum, under normal conditions, 3% dissociation. So the equation that you would use for calculating pH at a particular concentration of salt and acid, or you would use this equation to prepare a buffer, which you will do a lot in chemical reactions. You're going to prepare buffers for certain experiments, so you will be using this equation to know how much salt you need to add versus acid. Maximum buffering capacity occurs when pH equals pKa. We asked earlier, what is the pKa? pKa is the pH when you have equal concentration of dissociated and non-dissociated acid. So when this is equal to this, you have log of 1. Log of 1 is 0. and that's when pH equal pKa. That's the optimum or maximum buffering capacity. So at equivalence point, which is the end point of the titration, you will have number of acid equivalents equal number of base equivalents. We go back to that equivalence that we introduced earlier, which is very important because it determines your equivalent weight, which you need for the calculation. So at the end point, all of your acid has been neutralized. So basically, you will no longer have HA, right? When you're titrating with a base, your acid's continuously giving you their proton, then all of them will be dissociated. So all of a sudden, log A over a number that is very close to 0 will give you really high number here, and the pH will be increased rapidly. So you will see a rapid increase in pH at the end point of the titration because you no longer have non-dissociated acid, so this value will be very low. So you will be plotting titratable or titration curves in the lab, and looking here, you have 3 types and sometimes 4 types of titration curves. Here is a titration curve of a strong acid, let's say HCl. So this is a typical titration curve of HCl. So if we're using 0.1 normal NaOH to titrate HCl, HCl in solution is completely dissociated. So the pH is going to keep increasing as you add NaOH until you see a rapid increase in pH. The midpoint here, because of its rapid increase, the midpoint close to 7 is your end point. So the pH increases gradually as you titrate NaOH. So you don't see a plateauing, it's always increasing, and then an abrupt increase in pH, that is the end point. Whereas in acetic acid, there is a pKa of the carboxyl group is about 4.75 for acetic acid. So what you notice about the pH, when the pH gets to 4.7 or close to 4.7, you see some form of plateau. You have an increase, and then it flattens out a little bit around the pKa because here it's resisting change of pH. You're titrating, but you have a really flat kind of, and then beyond the pKa you start seeing increase until no longer you have the acid. They're all dissociated into conjugate base. You see a sharp increase, and the midpoint is close to 8.2 usually. And I'll tell you in a minute why it is basic. The end point is not really 7, it's a little bit higher than 7. And you would wonder why, because at equilibrium you should get neutral pH. But conjugate base gives you a basic pH. Because you have, when all the acid gives you their protons, you have salt. You have the carboxyl group in ionized form that is slightly basic. So the pH would be close to 8.2, 8.5. So here you have the citric acid. Citric acid, you have 1, 2, and 3 carboxyl groups. So you have 3 pKa's. So if you look at the titration curve of citric acid, you see plateauing around 3 different pKa's. So the pH resists change as you increase the volume of NaOH. You start seeing resistance of change around the 3.06, and then another plateau around 4.74, and another plateau around 5.4. Beyond a certain point, you see a steep increase in pH, and that would be your endpoint. Okay, we're going to stop here. Next time on Friday, we'll keep your papers with you. We will continue calculations on these papers next time on Friday, and then you turn them in.